Alright, I guess we'll get started, like, as people are coming in right now. So hope you all had like a good midterm this day. At least I did, kind of. Okay. So welcome back. And so this week we're going to talk about dynamic programming. And so I just wanted to announce first that like, we're probably going to spend a few weeks doing this. Probably two, like the next session will also be about dynamic programming. Wait, actually, let me see if how many of you have a previous done or heard about dynamic programming before? Okay, couple of you. Okay, so yeah, dynamic programming in my view is one of my personal favorite algorithms there. But another thing is that a lot of times when you learn something like a to give you an example, if you heard something like a Bell-Manford algorithm, which is one of the graph algorithm, or some other algorithm you heard about, a lot of times they are quite deterministic, I would say, in a way that once you basically when you see this code, so for example, when I search online, see the Bell-Manford algorithm, I'm gonna see the curve, the whole code for it. But dynamic programming is pretty different from that aspect that when you search online what is dynamic programming, it won't actually give you a very specific definition or specific code for what it is, because a lot of time dynamic programming really is about improvisation, and based on specific problems you have, you might have different kind of dynamic programming set up. So it's more like an idea rather than a specific type of algorithm we're learning today. So I hope that kind of makes sense here. Yeah, but with that being said, let's just get started. Okay. So this will be the first, there will be two classes about dynamic programming. This will be the first one. Janet? Sorry. Do you mind close the door? Is that you? Sorry, it's Jane or? Jane. Sorry. Okay. I met a girl yesterday, so. Okay. Alright. Okay, let's just get started. Okay, so let's just a quick before I talk about what is specifically dynamic programming is, I'm gonna say that there are normally two types of problems you want to do with dynamic programming. So the first type of problem you want to deal with is called optimization problem. So normally when you have, let's say, what kind of problem would be an optimization problem? So for example, you have let's say a graph, and you want to find the given one node, you want to find what's the shortest path to another node. That would be kind of an optimization problem in the way that you're finding the max of something or the minimum of something given certain constraint. So that would be kind of what generally will be an optimization problem. And that's the first type of problem you would probably want to consider using dynamic programming. And the second type of problems will be kind of related to exhaustive search. So so I know that exhaustive search, so it sounds like a pretty terrible idea when you do programming or doing algorithm design, right? It sounds like a pretty bad idea to use exhaustive search. But you're gonna see that when we're doing dynamic programming, a lot of ideas actually exactly the same as exhaustive search. But the trick here is that you have to use something a little bit clever. Okay, so you want to do exhaustive search in a clever way in order to solve the problem. And so we'll see later that when you do exhaustive search itself, the runtime complexity will be, let's say, n factorial, right? It could be exponentially growing. But if you say if we use something a little bit clever, let's say we do the exhaustive search in a clever way. I say overall illustrated what I mean by clever way, but let's say when you do the clever way, you can sometimes reduce it to the polynomial algorithm. So let's say n squared. This is a lot better than the factorial one. So this is the two types of scenarios that we would normally use in dynamic programming. The first one is just optimization, the second one is normally just an exhaustive search, but we won't do it in a clever way. So more specifically, the first session we'll talk about the four different aspects of dynamic programming. The first one is just a very generic description of what is dynamic programming. Basically, it's just using memorization and sub-problems. I will talk about what each of these means. And then we'll give two different examples. The first example is the Fibonacci number, which I believe if you heard about dynamic programming before, you probably already seeing how this problem can be optimized using dynamic programming. And the runtime complexity was originally, I believe, factorial or something. And you can reduce this to the linear capacity. So this is one of the optimization we have using dynamic programming. And the second example we'll be giving is using shortest path, which is the context will be that if you have a graph, and you have any graph basically, and you want to find the maybe there are some constraints like the weight might be positive, but we'll cover that part later. So given any graph, you want to find the shortest so from node A to node B, you want to find the weight of the shortest path. So that's what it means by shortest path here. So this is another optimization problem we will encounter using today, using the idea of dynamic programming in order to optimize it. And the last one is also a little bit generic definition here. It's called gassing, and this thing is DAG. So basically what DAG stands for is directly acyclic graph. So what a directly acyclic graph means that, so this is a graph, and it's directed because the edge has the direction here. And directed acyclic graph basically means that the graph is also directed, but doesn't contain any cycle, because that's what it means by acyclic graph. And view, I said this is something connected to the programming, dynamic programming, because as we will see later so the first problem is kind of just what generally how dynamic programming works. But you sort of want to pull another trick, which is you want to convert the dynamic programming into acyclic one in order to make it solve more problems than previously can solve. I'm going to illustrate what this last one means, but it's going to be the challenging part. It's going to be the last one. So the last two is going to be I would say that will be the challenging part for today. Okay, so with that being said, let's just get started on talking about what dynamic programming actually is. Okay, so far any question? Okay, cool. Alright, so I'm gonna give a brief equation of what dynamic programming is. But this equation will vary as we move on the class. So far I will define dynamic programming, or just DP, as being the subproblem plus reuse. What is a subproblem? A subproblem just when you have a problem, let's say it has a certain input. So a lot of times this input can be break down into smaller scales. That's what is defined as a subproblem. And reuse basically means that when you solve those smaller problems, and you kind of want to reuse those results, in order to make the further computation faster. So so far we have this equation, which is dynamic programming is equal to subproblem plus reuse. Okay, so we're gonna give the first example about Fibonacci number, which is which I would say is the easiest introduction we can have about dynamic programming. Okay, so the example is that, let's say if we have the following problem, which is f1 f2 is 1. Okay, so this is the first dynamic programming problem we have. So the definition of the problem is that f1 equals to f2 equal to 1. And fn is calculated by exactly the Fibonacci formula here. Fn is equal to the previous two terms plus together and minus 2. And we want to compute the fn. So this is the whole problem we have here. So any idea how to solve this problem using the any approach you might have? Any idea? Okay. I'm gonna say the first one. I'm just gonna give the solution called which I say is the naive recursive solution. Okay. I'm gonna write down the numbers here. So which is just a function which takes number n, which is the number we're calculating, and if n is smaller than equal to 2, then n example will be probably be pretty easy compared to the later ones we're gonna get. So it's just to like give you a general feeling like what a dynamic programming is. So this will be the naive like recursive algorithm we can have, which is the probably the most intuitive one. That if you have two cases, which one of them is base case, that n is smaller than or equal to 2, then in this case the output would just be 1, so which is corresponding to this part of the equation. And the other case is that, let's say if you have a n is greater than 2, then basically just f is equal to the previous two terms times together. And yeah, I think yes. And then you return f at the end. Is there any question with regard to this recursive algorithm? Okay, so any idea? Okay, so is the algorithm good or bad, you think? It's bad? Okay, yeah. It is actually pretty bad, right? Because it's actually exponential time. And the reason it's exponential time is because, okay, let's see how we can prove it's exponential. So given that one input, right? So the t, which I stand for the time to compute the value n, what is this equal to? Okay, so in terms of t, it should just equal to like the two subproblems, right? Because this one is just constant, right? The first step is all of 1. And the next two, these two, basically are two subproblems. And they both take about, using this notation, takes about, one of them is taking about n minus 1, the other one is t times t n minus 2. So this is like the time taken for computing the value at n, and it's equal to n minus 1, n minus 2. Does this make sense? Okay, so we can give like a pretty, so this part, right, we can make it a little like cleaner, which is that, so this one is t n minus 1, this one is t minus 2. We can just give it an upper bound, a lower bound, which is, so this whole thing should be greater than equal to 2 times t minus 2. Sorry, kind of hard to see. Okay, I'm gonna write over here. Okay, so the complexity of that thing over there is so the t of n is equal to t n minus 1 plus t n minus 2 and plus both 1. Right? And this part, so we can give like a lower bound of this formula, which is like this formula is greater than or equal to 2 times t n minus 2. Because t n minus 1 definitely is greater than t n minus 2. Okay, so if you have this, basically this is saying that, alright, and the base case is just gonna be the t0, which is the base case, it's just gonna be a constant, right? Because when you reach the base case, it just returns the first one. So t0 just equal to all of 1. Does this make sense? So each time, okay, so this is saying that basically t of n is equal to 2 times t minus 2. So what is t minus 2 equal to? It's equal to 2 times t n minus 4, right? Using the same sense, deductively. So 2 times t n minus 2, so we can write this whole thing as 2 times 2 t n minus 4. And so you can see why this is growing exponentially, because each time when you n minus 2, you basically have another factor of 2 multiplying each other. So eventually you're going to have like n, this part is going to be 0, but you're going to have a lot of 2 at front of it, multiplying each other. So more specifically, when you write this thing together, you're going to have all of the 2 to the time of n minus 2. So the rounding complexity of that, algorithm is going to be all of 2 to the power of 2 n minus 2. And the reason is because each time you n minus 2, you have a factor of 2. So depending on how many 2's you have, like how many 2 n has, you're going to be like 2 to the power of this. So this is why this is an exponential algorithm. Like this so far we have. Okay, and so what would be the improvement that we can have to make this algorithm better? Any idea? Okay, so the improvement, is actually kind of intuitive. Okay, so let's see why this algorithm is so bad. Okay, previously I said that like DP being defined as the subproblem plus reuse, right? And the reason why this algorithm is so bad is because when you're trying to compute the value of the n, let's say, so when you try to compute the Fibonacci number of value of n, you're basically computing the value of minus 1 and minus 2. And you're computing these two values. But when you're computing minus 1, right, you are computing minus 2 and minus 3. And when computing minus 2, you're also computing minus 3 and minus 4. Okay, you're gonna see that, so it's gonna be kind of strange because you actually already computed it. So it's supposedly, you actually would be already computed the minus 2 because you already did it here. But as a matter of fact, when you're doing this algorithm, you actually computed it again. So it's the case of minus 3. And as you can imagine, like as this tree growing, like a lot of things actually were overlapping. So a lot of computation were actually done like twice or third times. So the most like direct way to improve this algorithm would be use I say using a manual table. So I just would need to add one line in order to make this thing like a lot better. Which is that I want to add before this n minus 2 equals 1. I want to add before this line that if n is in the memo, then I just simply return memo n. And otherwise, after I'm done computing from this part, I want to memorize. Okay, so this is basically saying that if the n values are computed inside the memo, I just need to return the n value inside the memo. And if it's not computed, it's going to jump this part to this part, which I have to compute it, right? And after I'm done computing, I want to memorize this value, which is I want to do is memo n is equal to f. And this is basically allowing me to memorize this value inside this memo table. Does this make sense? So, okay, so why this like faster than like the reason is because if you think about it, okay, so when we're trying to compute, let me write it here. All right. So why is this algorithm faster than okay? So when we're trying to compute the value of n, let's say, right? All we need to do is just compute all of the values before n exactly once. Does that make sense? Like because if as long as you computed already, it's like gonna be like inside the memo table. You're just gonna have to retrieve it. So in order to compute the value of Fibonacci n, you just have to compute all of the Fibonacci from 1 to n. So it's actually gonna be linear. So okay. All right. Does it make sense or okay? So okay. So why is this? Then why is this like using DP then? Like the reason is because you actually have a lot of subproblems. In this case, you want to compute the value of n. So you want to do all of the value from 1 to n. So those would be the subproblems you have. And more specifically, if you write it as a graph. Okay, so more specifically, if you write it, try to write it as a graph. Okay, let's see. Okay, we want to compute the value of n. This is the value of n. So this is minus 1, minus 2, and so on. Okay, so this is the thing that you're trying to compute, and this is the value you want to compute. So the value of this relies on these two values. So I would say they have dependency on these two values. And this one has dependency on these two values. One is in n-3, the other one is in -2. And this one also has dependency on these values. So you can see that, okay, so all of this kind of, the value you want to compute have pre-dependency on these values. So this is actually what I mean by how dynamic programming can be related with directed acyclic graph. Because if you see here, all you have is so the way we're computing it is actually this is actually a acyclic graph. Okay, so you won't find any cycle inside this graph. First it is directed, and then you won't find any cycle. But we're gonna see that like later on, especially the second problem, the shortest path problem, it won't be this easy because you actually have cycles inside the problem. And this one it doesn't, and which is a good thing because all you need to do in this one is just using a loop. Like you go from so when you use a loop to compute its value, you just go from n is from okay, so you basically just go from a loop and you go with from 1 to I from 1 to range of n. So you go basically use a single loop from use value from 1 to n, and you go all the way up. Like each time you compute if I is smaller than 2, then otherwise just equal to I minus 1 and I minus 2. So okay, so the reason I'm saying that is because in this case all you have is just a directed graph. So if you see like the tendency of them is like a cyclic. So all you need to do is just use a loop, like go right forward, like all the way. But when you have like a second problem, which is the shortest path problem, it won't be this easy. We're gonna see like in a minute why is that the case. But any problem with this like example, like with the Fibonacci number? Any problem with like how you can like think of dynamic programming in this way? Like you have to compute the previous values first before reaching the value in. Yeah, this is what I mean by dependency. Also, okay, so this is the equation we previously have, right? It's the subproblem property reuse, and now you want to plus its memorization because you want to use a table to memorize the result you previously have. Or specifically, you want to memorize all the subproblems you calculated before, which is the problems of a smaller scale in order to use it for the bigger scale problems. So the equation right now is subproblem plus memorization plus reuse. Okay, so yeah, this is like probably the easiest example of dynamic programming. And if you recall that previously we used like a recursive approach and with like a memo table, right? Okay, that's okay. So any problem with this part? Okay, so Fibonacci number is probably like one of the easiest, like the most intuitive one example we can have like with dynamic programming. Okay, so the previous one we used basically we used recursion in order to solve the dynamic programming problem. But right now we're gonna use like something called a bottom-up approach. So these two are exactly the same. So the bottom-up approach and the recursive algorithm, they are exactly the same approach. Except, so when I finished writing the recursive approach, right now I'm doing the bottom-up approach. I don't even have to think about it. I just have to like write it down. That's like because they are exactly the same thing. So when you're doing the recursive approach, you start with the problem you're trying to solve, which is n, and you break down into the subproblems like each time you're doing recursion. Go to different like frame of functions, like smaller frame of functions, and eventually reach the base case. That's how you do the recursive problems. And in the bottom-up approach, you want to use a loop, and you want to start with the first, like the also the base case, but you want to build it up instead of like going from up to downwards. That's the only difference we have here. And the normally during the dependent programming, because they are similar, sometimes it's easier to think in the recursive approach. But whenever you can, you actually want to use the bottom-up approach because it involves less function calls, and that's more efficient for using dynamic programming. Especially have like thousands of like say function calls, that's actually gonna cause some stack overflow. But if you use the simply a loop, that won't be a problem. So whenever you can, you want to use the bottom-up approach instead of using the recursive approach. So but they are exactly the same. In fact, this case, all I need to do is just to define a loop, and I want to start with the base case, which is 1 and 2. 0 and 1, right? That's the base case for Fibonacci number. And both of them will just be 1, and the subcase will just be the previous I minus 1 plus I minus 2. so this is what looks like for a loop. So it's very similar to the case when you have a recursion. Yeah. Does this make sense? Like the bottom-up approach? So yeah, it's similar to the recursion. Okay, now we're gonna do something a little bit more interesting, which is instead of doing Fibonacci, we're gonna move forward to the shortest path problem. Let's see what time here. Okay, we have plenty of time. Also, the reason I said like dynamic programming doesn't have like a general framework or template is because like all of the problems have like different setups. It's more like an idea rather than a specific algorithm. It's like a designing something rather than something you can memorize directly. That's why it sometimes takes so long to like master what dynamic programming is. Like for example, if you learn Bell-Ford algorithm or some like simple like graph algorithm like depth search, you can just pretty much you don't even have to understand like what it means because all you need to do is just like see what the code is and you just basically copy paste. But dynamic programming is completely different. It's each time you can apply dynamic programming in a lot of problems, but all of this code or different problems will look different. So that's like the core part of why dynamic programming can be hard. But also it's very extremely flexible. So some of the hardest problems, like say some of the like extremely hard problems, such as the so this shortest path problem, which is if you've ever heard some algorithm like I talked about, it's called a Bell-Ford. So this Bell-Ford actually he wrote this paper called dynamic programming, and the initial reason for why he called this thing dynamic programming is because he was actually doing something that's so he wanted to make this thing fancier. That's one of the reasons. That's literally one of the reasons why he called this thing dynamic programming. So it actually has nothing to do with programming. So in England, I think England, or like the history is that like programming basically means optimization. So and dynamic means that this thing is related to the time. So which stresses that like this thing has states and it's changing constantly. So that's why he named this thing after like dynamic programming. But it's really a very flexible term for algorithm design. So a lot of really hard problems which can only be solved using like if you have hard problems and it can be solved in polynomial time. Normally, that dynamic programming is the way to go. So that's how like important this algorithm is. Like generally the idea of how important it is, but it's really there's like a variety of like variations for the form of dynamic programming. So the second one I'm gonna see is called shortest path, and this one is literally the Bell-Ford algorithm, which is allows you to find the shortest way from one single source to all of the other nodes. Let me think. Yeah, from one single source to all of the targets. So I'm gonna illustrate what that means in a second. But so for this algorithm, this actually where originally dynamic programming, came from. So it came from the Bell-Ford algorithm by Bell-Ford himself. So yeah. So this is also the second example. Okay. So let me see. Okay. So any questions so far? Like I know it's maybe kind of confusing because especially if you never encountered dynamic programming before. And most of the time when you let's say if you want to do the code force problems or like some really challenging platforms, so most of the really hard problems will actually be about dynamic programming. And the reason is the same that so remember the first one we had before, which is about Fibonacci number. It using a memorized table, right? It's probably can be using an array. But this is only one-dimensional. But some really challenging problems, give you an example, just could use multiple dimensions to memorize the separate subproblems. And you want to retrieve those problems from those tables and want to reuse those solutions. But those are the really challenging dynamic programming problems. You can find a lot of really challenging dynamic programming problems on any platform. So alright, so we're gonna go to the second example of dynamic programming, which is about shortest path right now. Okay, so the problem we have is that let's say so we have a graph. Okay, so the problem we have is graph. So graph is just like a bunch of nodes and connected with the edges. In this case, we have connected edges. So it also could be unconnected. Just the unconnected edges, just like double direction. That's it. And but in this case, let's just assume that we have directed edges. So you have a source, which is stands for like as source is the source, and you have like an end, destination sort of. So you want to go from the source to the end, and you want to find the shortest path among all of the possible paths. And more specifically, each of these edges has a weight. So it could be weight 1, 2. So a weight is basically just a number indicating like how long this path is. So in this case, it could be 1, 2, 3. And sometimes it could be negative, but in this case, we just consider like it could just positive numbers. So yeah, that's what the algorithm means. So let's say if you have one target node and one like source node. So what do you think is the idea here, like to use dynamic programming in order to solve this problem? I know it sounds completely irrelevant with Fibonacci number. Like it's a completely different setting, like in graph in this case. But how do you like think about using dynamic programming? Okay, I'm gonna give like you probably 5 minutes to think about this. Sorry, 3 minutes actually, because we got a lot of time today, and also just this is a completely different context here. Just it's a little bit real. So this all could be added. How would you come up with an algorithm to find, like, go to this place? Yeah, not so easy as Fibonacci right now. Yeah, any idea? Yes. Sorry, did you raise that?
Yeah.
Yes.
Maybe you try like so from node S to node B, for example. Then we just try all the nodes in between them, starting from like the second last.
Starting from the second last.
The second last.
Okay.
Yeah. And like see the distance from S to that.
Yeah.
Plus the weight of the last edge is like smaller than the distance from S to B. And the updated distance, like updated minimum.
Oh, I see. Like, let's see if I get what you mean. Okay, so basically saying that, suppose that all of these nodes connect to the target node you are going to. All three nodes, these 3 nodes. So you want to basically try each of these nodes.
Yeah.
And then see from S to all of these nodes. You want to find like what would be the minimum distance from S to all 3 of these nodes.
Yeah.
And then like find out, compare all of them and see like which one is the smallest.
Yeah.
Okay. Any other idea? Okay. I'm just gonna say. Okay, this is actually okay. I'm gonna say first that this is actually exactly the same approach, but I'm gonna say that actually before I say why it is so, but I want to say that so a lot of the time when you're doing the computer science problem, especially when you don't know the answer, you want to try things, you want to guess things. That's actually literally the best way possible. Do you remember like the last time when I was I don't know like when I was giving this problem, like it was about binary search, and it was like a tank. So, but we were using binary search to do the guesses. Each time we like eliminate half of the answers from this range, and that's like basically also using the same trick, like guess the answer. So in this case, exactly you want to guess all of the possible outcomes, but if you want to make like each time you make a guess, you want to sort of eliminate your answer like a little bit. So in this case, okay. So you know that you want to go from S to B. And you know that one of the paths is gonna get you the shortest path, but you don't know which one. So let's just say like you have 3 possibilities, right? Because B is actually linked with 3 other nodes. So each of these possibilities, you don't actually know which one will give you the shortest path. you're just gonna like record all of them. And basically let's say 1, 2, 3. So you don't know which one of this door leads to the shortest path. You want to record all of them as being one of the possible results. And then right now the question becomes, instead of reaching from X to B, you want to go from X to one of these 3 doors. Does that make sense? And of course, I mean, okay, so all of these 3 different nodes has a weight of cells like W1, W2, W3 to the node B. So you actually get a smaller problem, which is not from X to B, but you get a little bit step further, like which is you go from X to one of these, like all of these 3 nodes. Does this make sense? Okay, so basically, so what about after this step? Like how do you let's say so you want to go from S to B previously, you want to now go from S to one of these 3 nodes. And the next step is gonna be like exactly the same. You want to try like what would be the shortest path from S to this node. So you want to find all of the nodes connected to this node, and which is possibly a lot. And you want to see from S to one of these nodes, like what will be the short distance then. And eventually, okay, let's say we go all the way back, which is eventually you find that some of these nodes link to S directly. So there's no need to go like all forward from that. It's already reached the S node. But that's the general approach we do here. Does that make sense? Yes.
How is that dynamic programming?
How is that dynamic programming?
Exhaustive search to me.
Sorry, what was that?
It looks like exhaustive search.
It is exhaustive search. I mean, okay, so it's kind of tricky, but I said before that, so dynamic programming I used in 2 different cases. One case is using optimization, which is like this is probably optimization, but it also can be used for exhaustive search. But the trick is that you want to do it in a clever way. And the way I just described it, okay, actually I didn't ask you, but like, do you want to use some kind of a memorization here or not? Just using this completely like recursion thing, because yeah.
Yeah, I think like in visualize like a 2D array. The first one is the source, and the second one is the endpoint.
Okay. Okay, so you want to use the memorization. Okay, exactly. So this part, the only difference you have is that if you don't use this table, it's gonna be an exponential algorithm because each of the nodes is gonna have different outcomes, like at least a few outcomes. Like and all of this will lead to other outcomes. It's gonna be like an exponentially growing tree. So it's actually pretty bad. But I mean, but okay, if you don't have this thing, like okay, so let me think about how is that different from like let's say the like exhaustive search here. So let me give you a brief example here. Okay, I'm just gonna illustrate what is the difference here when you use the table and when you don't use the like memorization table. So let's see what the difference will be. And that was a really good question, by the way. I didn't actually think about writing that down on my notes, but I think that's worth answering here. Okay, so yeah, let's see what's the difference here between using a memorization table. In this case, it's a 2-dimensional array. You want to record the shortest distance from the S to B, which is V is so B is basically for all of the nodes. This is for all B in N. Okay, so let's see what is the difference here between using memorization table and not. Okay, so okay, so I'm not sure this, maybe this will be better. Okay, so I'm not sure this is a good example or not, but okay, let's just give it a shot. Okay, so let's see, this is the source node, and this is the destination node. It's kind of ugly, but let's see, I hope it works. Yeah, I just came up with this example a few seconds ago, but I'm not sure it works. But okay, the point that I'm trying to make is that you want to use memorization table because you don't want to do extra computation. In this case, okay, let's see. Okay, there you go. This will be better. Okay, I think this will work. All right, so you want to go from the source node to the destination node. That's something you want to do, right? So the reason you want to use a memorization table is because you want to go from the destination node backward. As you want to you know that you reached this node eventually. So you want to go from this destination node backward so that you want to find what will be the second next node you want to go. So which could be both of these nodes because they both lead to the destination node. So okay, so we go to here and here. We want to try to find what's the minimum distance from source node to these two nodes. That's the thing that we're looking for now instead of a D. And then basically we go a little bit backward, which is from this node. You want to find, so this node is connected to this node. So you go back, you see this node, what is the shortest distance from S to this node? That's the thing you want to find. Okay, so the difference comes exactly here when you use memorization table and when you not use. The difference is that when you go to this node, you are trying to compute what is the short distance from S to here. Then if you go back, okay, let's see. If you go back, you check these two nodes, right? You try to see what is the shortest distance from S to these two nodes. I mean, which one of these is shorter? Because you want to go here, and the way to go here is from these two nodes. So this time is when the memorization table comes to use because you find that you already computed distance from S to this node. Because you did that already when you go to this source node, right? So in this process, you already computed this part of the answer. So when we're trying to compute from S to here, you go back to these two nodes and you don't actually compute this thing again. You just simply do this part only. Because this part you haven't computed yet. So this is the beauty that this is only a acyclic graph that in a way that, okay, so each time you compute the value from source node to this node, you don't ever compute it again. But if suppose that you don't use a memorization table, instead of use an exhaustive thing go backward all the time using recursion, then you would have to compute this value again because you didn't memorize it. But that's the only difference I would say is using this memorization table. Yeah, but if you don't use it, it's just going to be exponential because each time instead of going backwards, it's going to be going exponential. But if you use if you use a memorization table, the distance from source node to each of these nodes is just linear. Okay, so from source node to any node, the distance is just computed exactly once. Does that make sense? Or because if you go backward, okay, so this value is not computed, so you go backward again. And this time you find that the value is computed. So once this node is computed, you automatically know this node. So all of the node is computed exactly once and is stored in the memorization table. You just have to retrieve it. You don't have to do it ever again. Does it explain why it's different from exhaustive search?
And what does the runtime drop down to?
Sorry, what's that?
What does the runtime drop down to?
Oh, for this one?
Yeah.
For the development for algorithm?
Yeah.
Actually, the algorithm we currently have, right now, the runtime is O E plus B, where B is number of vertices, E is number of edges. But as we'll see very soon that this is incorrect. Because the development for algorithm runtime is O times VE. So it's slightly bigger than this. But that's the next question I'm going to have, why is this algorithm incorrect? Okay, so the solution proposed by Kwon, right? Yeah, why is the solution proposed by Kwon not correct? Any idea? This is the tricky part, literally the last part, but it's gonna be the tricky part, but why is this part incorrect? Why can't I just compute the previous value each time and go backwards all the way to see the source node and then when I know the answer, I just suddenly know everything. Oh, I hope I made it clear, but any idea why this is incorrect? The current runtime algorithm, runtime is just going to be E plus V. The reason is because we do every node exactly once. We go every address exactly, linear time at least. We go all of the address exactly linear time. All of the nodes we go through only once, computing only once, stored only once. So the current algorithm we have is O E plus V. And the development for algorithm is O VE, which is way bigger than ours. is the product of them two, rather than the addition of them two. So where went wrong? Like, any idea? So I mean, first of all, do you think this is a good algorithm or not? Like the one that's proposed by Cole? Or is there any like problem with it? Little problem? It's not that obvious. But
Do we consider like there are cycles?
yeah. I mean, this one no, but like what about cycles?
Oh yeah, so like if we have like a negative cycle, then if we just go along that cycle, the path is just wrong.
Exactly. Okay, let me illustrate why this part is wrong. But okay, before this, this example we have that doesn't contain a cycle. Okay, let me illustrate what would happen if it contains a cycle. Okay, and just before that, let's say like if it doesn't contain a cycle, this actually is a really good algorithm because the runtime complexity is linear, right? It's time e times e plus b. So this is literally the fast algorithm there is. I think there is a fast algorithm. Oh, by the way, so the Fibonacci example I gave before is the runtime complexity for that one is O of n, right? It's the n is the number of Fibonacci number you can compute. But there's actually a faster algorithm than this, which is using O of log n. But we're not going to cover that part today. But I'm not actually sure that how this part is implemented. But n is already pretty good compared to the exponential part. Yeah, I'm not sure log n is using dynamic programming or not, but yeah, just a quick mention here. Okay, so but for this part, for this problem, the algorithm we have here, if it only for the directly graph and without a cycle, this is a really good result. We achieve the linear time. But let's see what happens if there is a cycle. Okay, let's gonna see the interesting part right now. Also, they might be like okay, the next example, like the next few minutes is gonna be kind of confusing. Hope you're ready. Like, okay, the previous trick we did with the Fibonacci number is pretty much the whole idea of dynamic programming, just using memorization. But the important part is that when you solve the sub problems, right, you want to do it in a correct order. And the reason is because when you don't do it in a correct order, you're gonna run into issues. Let's see why is that the case. But the whole thing is still about like memorization and sub-problems reuse. Those three keywords. And guessing also, like 4 keywords. So sub-problems, reuse, guessing, and memorization. So those 4 different keywords are the core of dynamic programming. But the next keyword we're gonna have is in the right order. And you're gonna see why is that the case in right now. So let's see if we have this example. So this is source. Alright, so this is simply it's the very simple example, but it tells a lot of the problems about this implementation algorithm we have right now. So we have the source node and we have the destination here. And these two are the intermediate ones. So you want to find the shortest path from the source node to the destination node. So what would be the first thing you do, like in this case, like using Bellman for algorithm? You want to make a guess of what will be the last edge you reach, like what will be the last node you reach before reaching the destination, right? And in this case, okay, so the destination node is the only incoming edges is this one. So the only possible way you can reach from this destination node is from node A. Right? Does that make sense? Okay, that's the whole idea behind going for algorithm. Also, guessing comes in the way that you want to guess what's the last node you went to. That's the guessing part. So in this case, there's only one node, so you don't actually guess it, but in the case that there's a lot of nodes, you want to guess exhaustively which one of the nodes you went for the second node. Second last node, yeah. But in this case, it's not guessing because there's only one possibility here. So okay, so let's see what would be the following force algorithm doing here. So the first thing you do is that you from the source node you want to go to the destination node. It's from S to B. And then you find that, okay, so you make a guess, you see that this is the last node you reached. So basically this time you go from S to A. Right? This is because this is definitely, if you go there, this is definitely the last node you reached. And you want to plus this with the weight of A to B. Because the A to B is just the last edges you go. So you want to, right now the problem is that you want to go from here to A and then from A to B. Okay, so far so good, right? Okay, so the next part is that you want to go from S to A. Then you want to guess which node leads you to A, right? In this case, it's like there's only one incoming address from to A, which is B. So the problem immediately becomes obvious that you want to find from S to B. You want to go from S to let's see, S to B is oh yeah, you want to go from S to B, and then you plus the basically weight of A, B to A. So does this so far is it good? Does it make sense? Okay. So you want to go from source node to this. Basically go through all of these steps. Okay, the next part is the most interesting part. Okay, so right now you want to go from node S to node B. So we're going to go from here to here. This is where the interesting part comes from. Okay, this part. Okay, what do you do when you try to compute this part? So you want to guess which part leads you to B, right? There are two possibilities. One incoming edge is from S to B. The other incoming possibility is from B to B. See where the problem is? Okay, let me just write it down. So there are two possibilities. You want to try them exhaustively. The first one is that you want to try from S to B. The other ones you want to try from V to B. Oh, no, never mind, sorry. This should be S to B. So in this case, you have two possibilities written here. So one of the incoming edges from S, the other one from V. So one possibility is that you want to go from S to S itself, right? Because that's the last node you go to. So you want to go from S to itself. The other possibility is that you want to go from S to B, and then you go to B. These are the only two possibilities. Okay, any idea why this is wrong? Where's the problem here? Any idea? Yes.
You would keep going in a loop, like because SV would go back there.
Exactly.
Yeah.
Okay, so that's the problem. So you see that we are trying to compute SD, and we are doing a lot of subproblems here. But as we go deeper and deeper, we find that we are actually encountering SV again. So the problem is that you're trying to find the value, but you're using the value you're trying to find in order to generate this value. So this will leave exactly the whole tree like over this again. So this is actually an infinite loop. So this code in this case will never terminate because it contains a cycle. So you have to keep computing these subproblems. It never ends. So this is what I mean by you want to do the subproblems in a correct order. So order in this case matters a lot because you don't want to so when you are trying to find a value, you don't want to use the thing that you haven't calculated yet, because that will lead to infinite loop. Because you're basically just calculating things using the thing itself, which is a paradox. So yeah, that's the problem we have here with a cycle, which contains a cycle. That's the problem here. Okay, so any idea how to fix this thing? Then? Still using that programming, but want to fix this thing such that it's done in a correct order and doesn't contain any cycle. Yes.
Keep explore the nodes that we've visited already, basically.
Okay, so you say that. Okay, let me just basically rephrase what you say. So you basically say that instead of simply using a map, you want to add another variable here. Keep sort of how many nodes we have already visited.
Yeah.
That's the solution. Exactly the solution. Okay. But before doing that, I just want to mention that. So also another reason why dynamic programming is challenging is because sometimes it's very hard to find the correct order of solving the problem, especially the correct order of subproblems that leads to the answer. And this is one of those few cases. Okay. So in this case, it's actually a trick that we're going to use is that you want to add a third dimension. In this case, is that you have x to b, you want to add a third dimension, it's like this dimension, name it k. So the table becomes like 3 variables in this case. So there's the source, there's the destination, and there's the k. So k basically indicates like, okay, I'm gonna say that instead of how many nodes you visited, I'm gonna use the say that how many addresses you uses. So here we're just counting that how many times you go back. So exactly the same thing, but I'm just gonna say that k here indicates like how many addresses you have previously visited, like how many addresses you're using. So it's actually exactly the same thing. Does that make sense? So instead of k here denoting like how many, I say, so from B to like A, this is using 1 dash. But also could be like using, let's say, let me see what this. Okay, so from, let's say, okay, so, okay, let me try to think about how to explain this. Okay, so let's say there are 2 ways to go to this. Okay, so this is A, this is B, this is C. So there are 2 ways to go from A to C, right? One way is just go from A to C. The other one is A to B to C. And the other one, like the nodes in this case are supposed to, but I could add this also like exactly the same. But yeah, and that's just to say like we're gonna use like how many nodes you have already visited before. Okay, it's actually the same thing here. But the important trick we learned here is that we want to use the third variable in order to make this acyclic. Okay, I'm gonna give you a very confusing graph in order to show you that why this thing works after you add this third dimension. And also, by the way, this is the last part. We get what I'm saying. Like we use guessing and we use something called directed acyclic graph. And I said, oh, this view is erased. Sorry. So this is the view. This is not so dynamic programming itself has nothing to do with the directed acyclic graph. I'm just saying that in order to find the right order, you want to make it like acyclic, so that you want to compute the things that don't have to do it like you want to find the thing instead of computing over again. So don't induce any like include loop. Yeah, that's what is why it has something to do with the direct acyclic graph. Okay, I'm gonna give like a very confusing graph right now. That illustrates why after you add the third variable k, it solves the whole problem. I mean, basically why it adds basically why it adds the sk, it basically makes this graph acyclic one. So okay, so I'm gonna say something crazy that this graph is actually exactly the same graph as this graph, but it's the acyclic version of that graph. Okay, so it's kind of hard to so the reason why this is the case is that you want to sort of explode this graph into layers such that it preserves the edges properly. You're gonna see that, so the way I make these edges, like this different edges, it preserves the structure of the graph. So let me give an example. This is the start node. So you can go to B and you can go to this node. Or you can start with this node. And so there are basically 3 ways to traverse this graph. And exactly this corresponds to the different 3 ways of starting points of traversing the graph. And okay, the reason why this is related to that is because we add a third dimension. This is the layer, and this is the layer, which you can call the time series, which is just called time. So each time you make a traverse, you go 1 layer downward. This is what it means by k. So at first the k is 0 because you use the 0 address, and then you go traverse once, you go 1 layer below, then you go 1 layer below. This is the most frequent strategy we use in dynamic programming, which is just literally you introduce a third variable And by doing this, this allows us to turn the graph into an acyclic one. Yeah, this graph is kind of confusing, I know, but okay, the trick here is that you're gonna see that this graph preserves exactly the same property as this graph, except that the start, depending on the starting node, like say this one, right? So you can see this graph has actually 3 different graphs because so from this starting node, you go to these different nodes. So if you start from here, there's no way you can reach here because there doesn't exist a path to here. So that's why it preserves the perfect structure of that. So some of the nodes are actually the same. So for example, this one is S, this one is SOS. But they are different S's. Oh, sorry, I didn't mean to curse. But I'm just saying that there's different starting nodes depending on the way you traverse. So you explode this like directly graph into undirected ones. Sorry, you transform this cyclic graph into uncyclic ones using this kind of trick, like by exploding it into different layers of graph, but preserving the same structure of that one. And the downside is that you introduce a third variable inside of the like in table, which is k. And let's say this one, k is going to be equal to 0. This one is 1. This one is 2. And in this case, okay, the worst case scenario is just k is going to be 3 because k is going to be 4 because you can't like if you can't go to any other node, you basically just go to like exactly traverse exactly once. And I say like because like in this case there are only 4 nodes, right? You can't actually go to like the shortest path from S to B can be 5 nodes. Does that make sense? Because that's already redundant. So in this case, the k number of nodes you use can no more be 4. It's definitely less than 4. Because let's say if you go from S to B, so the shortest path cannot contain more than 5 nodes. Because if you contain 5 nodes, then definitely means that there's one node that's redundant. Yes?
Why go through this complicated process of converting the whole graph if you can just keep storing all the nodes that you have visited? Just say don't visit the same node again.
Let's think about that. So why do we introduce, this question is like why do we introduce this k variable?
Yeah, instead of just a list of all the nodes that you visited.
Instead of a list of
Or a set, let's say.
a set, okay. Okay, let me think about it. Yeah, I mean the problem is that well if you use a set, then how would you like avoid the problem that you are trying to like let's say okay. So you would still traverse it backward, right? So you will find that if we introduce a new variable, the order we solve the problem actually changes. So we no longer solve the problems in the same way that we did before, which is you go from the like destination node backward once, and then goes from this to once. So if you write down exactly like so in this case k is starting from 1 to like incremental, right, each time. So if you go through this part, you actually find that the order we solve the problems actually changes. That causes the fact that we'll have to like computing something that we didn't compute before. But if we use the set, like if we use the set or a list instead, the order for traversing problems didn't actually change. So the reason we introduced the third variable is because we want to change the order we solve problems, which causes like problems if you don't. Because if you don't change the order we solve problems, it's gonna introduce that kind of infinite loop thing. You're basically like computing the values that you didn't actually previously have. But if you do this trick, if you make the graph acyclic once, each of the dependency you previously computed, it guarantees that the previous like dependency you want, it's definitely computed already. Does that make sense? Or
I think I'm trying to look at
yeah, that's the hardest part of it. Okay, so dynamic programming, the Fibonacci one is extremely straightforward. The reason is because if you write the dependency graph of Fibonacci numbers, it's starting like ends destination and minus 1, and minus 2, and minus 3. You find that the way you traverse the graph doesn't actually matter because you're just computing them in order, right? So in this case, I'm saying that you want to compute n, you need these two values. You need these two values, then you need to compute like previous ones. And all you need is just a loop, and that skips all the things. That's why you don't need a third variable. But in this case, the dependency is not this straightforward. It contains certain cycles. So if you do the same trick like as you did in the Fibonacci number, since it contains cycles, it involves infinite loop here. But once you have this kind of exploding trick, introducing a third variable, the order of traversal changes such that you don't have to compute the values you don't actually have. Like you don't actually have this cycle. You basically make it an acycle. Yeah, that's what it means the last part. And this is literally the most challenging part of dynamic programming. But also why it's like a lot of time. I say if you want to do the palindrome, which is gonna be one of the problems we do next session, you also want to introduce like pretty much I would say all of the hard dynamic programming problems which involve you have to use this kind of trick. Like you want to introduce a third variable, so as to make the whole graph acyclic. Yeah, it's also why it's so hard. Like I mean I was kind of shocked like when I first saw this two graph like isomorphically the same. I mean maybe isomorphic is not the same like best word here, but basically it's preserved the same structure, and also it's it makes it acyclic. That's why it's much better. Like especially at least in the dynamic programming view. Yeah, but if you back to your question, let's say if we use a list or a set. Okay, so the reason why we don't want to do this is because it still doesn't like change the order you traverse things. Like the order will just be like the original Bellman forward way. Then you go back to the previous two nodes and then you go back. But this way is different. You might want to like maybe we can find the timing like maybe we can get like try to write down like how these two procedures are different. That will actually make things a little bit like more clear. Yeah. Rather than just seeing like very high level why this is the case. Okay, but with that being said, okay, let's just consider like right now, after introducing the third variable, what's the change of algorithm? Okay, so the downside of introducing the third algorithm, like the third variable, is that first the size of the table gets bigger, right? Because right now you have 3 variables instead of 2. So previously it's probability 2-dimensional, but this time it's 3-dimensional. That's one of the downsides. Which is I wouldn't say it's downside. It's just gonna like necessary to introduce the third variables. So the whole array is gonna be bigger, and then also the time complexity is gonna be v times the previous ones, because this is literally all of the possible values of v. Right? K is the number of nodes you traverse, which could be from 0 to all of the nodes, from 0 to v. So for each of them, so you have to times v to the previous complexity you have, which is e times v, e plus v. And I believe, actually let me check, what is the complexity of 1/4? I think it's okay, so the complexity of 1/4 is all of the ve. Okay, I believe that, okay, actually, I think I made a mistake here. So the previous acyclic ones, the complexity is all of the e. And so when you times v to this, the complexity of the Bellman forward is ve. So yeah, this is where originally the Bellman forward algorithm came from. It came from dynamic programming. And as a matter of fact, if you take any other graph class, you're gonna also learn the Bellman forward algorithm, but not from the dynamic programming view. But this is where the dynamic programming view originally came from. So it's from that Bellman forward. So if you only learn the Bellman forward, it's probably not that intuitive. Why is that? How does it work? But this is actually where the dynamic programming comes into place inside the Bellman forward. So this is the right complexity we have here, which is the O of the v times e, rather than previous ones, which is the O v plus e. Sorry, which is the O of e, which is simply like the number of edges. I mean, of course, I wish this is better. I wish this is the case because this will be way better for our life, but this is the reality here. So the true complexity is going to be all VE. So yeah, that's the Bellman forward algorithm we have from the dynamic programming view. Yeah, I believe also it's going to be kind of tricky if you first learn dynamic programming. And as a matter of fact, I think I learned it probably 3 years ago, and I still have difficulty of solving some problems. Given the solution I have, I don't kind of understand it. That's just how kind of unintuitive sometimes can be. Yeah. But yeah. Any question with this part or any other? Okay, let's see what time is it. Oh, okay, it's exactly 4:54. Okay, that's good. Okay, cool. So I guess I will probably maybe solve a few problems that's not really challenging, but it's gonna be related to dynamic programming. And I will send you guys like email for that. You guys try to maybe have fun with it. But yeah, that's basically that programming. Yeah, thank you very much. Have a nice weekend.